All right, good morning, guys. Today we're going to start on Unit 2. So this PowerPoint is going to be on properties of water, macromolecules, and enzymes. For this particular recording, I'm only going to be going over the properties of water. We're going to go through that first, and then we'll go through macromolecules and then enzymes in that order. So let's jump in. All right, so just to start this whole off, we got to start with a little bit of chemistry. You guys learned this stuff way back in elementary school about atoms. So in the picture here, there's an atom. In this atom, so an atom is a basic unit of matter. Matter is anything that's going to take up space. So literally everything in this room, myself, everything is made up of atoms. Thousands, millions of them, anything that takes up space. All right, and then of course an atom has three pieces to it. So in the picture here, I'm going to highlight what I'm saying. So this blue thing, well, let's say the blue things here, those are going to be your protons, all right? And then let's say these red things here, those are going to be your neutrons. And then these black things on the outside, those are going to be your electrons. So that's how those go. So your protons here, they're going to be your positively charged particles. And then the red ones, they're going to be your neutral charge. So they don't have a charge. And then on the outside here, you have your electrons that are negatively charged. Usually the protons and the electrons usually have the same amount so that they balance out the charge of the atom. All right, now the main thing here though is that you need to understand the electrons just so you understand what's going to be going on as far as the water molecule itself. All right, so this is kind of a really important picture. I also put this picture on your worksheet because again, it's pretty important to understand a lot of the properties of water that we're going to be talking about. So first things first, you should know that the formula for water is H2O. You should know that by now. H2O. So again, here's your H's, and then the 2 there that's by the H represents the fact that it has 2 of the hydrogen elements, and then right here, that's the O, the oxygen. So H2O is 2 H's, 1 O, and that is what the water molecule looks like. All right. Now, as I was talking about the electrons, they're on the outside of these atoms. And what happens is those electrons help for these guys to bond together. So what happens is they form a covalent bond. So a covalent bond is when atoms share an electron, the negatively charged particle. So again, on the outside here, I would say there's another picture that we use in chemistry that you can see it as far as like how we represent it, but usually we represent it by 2 dots. So these guys are sharing 2 dots. So they're sharing electrons, and these guys are sharing 2 dots. They're sharing electrons. And what happens is because they're sharing those electrons, this oxygen becomes negative because it's now thrown off an electron, and hydrogen atoms only have 1 electron. So when they have to share it, they now have nothing on the outside and they pull a positive charge. When you go into chemistry, you'll understand that a lot more. But for right now, all I need you to understand is that this water molecule is half negative, half positive. All right, so they're almost like a magnet. One side of it is positive, one side of it is negative, and that's really important to understand some of the properties of water. So a hydrogen bond, so right here, a hydrogen bond is formed when the partially positive hydrogen, that's this guy, and the partially negative oxygen or any other partially negative particle comes together. So again, because they're both sharing this partial charge, and mind you, they're partial charged because this hydrogen is also connected to this one. So it can't give full attention to this one. It's partially giving its attention to this one. So that's why they call it a partial charge. So remember that they're partially charged and they're connecting to each other. So that's that hydrogen bond, and it usually only occurs with the hydrogens. All right. Water is a molecule. A molecule is a structure that results when atoms are joined together by covalent bonds. All right. Water is a polar molecule. So that's like the really big important part. Water is a polar molecule. This means that it has a partial negative side and a partial positive side. And yes, it's like a magnet. All right, so let's bring that back. So referring back to water being a polar molecule, again, having that positive and negative side like a magnet. Polarity for water means that it's very attractive. All right. Polarity for water means that it's a very attractive molecule due to the fact that they can attract both negative and positive atoms. So they can attract a positive atom on one side, a negative one on the other, and then if they're attracted to each other, they just keep attracting each other because positive, negative, positive, positive, and they're just attracting each other. So thus giving this a great property called being a universal solvent. Right? A universal solvent is a solvent or a solution in which many solutes like salt or sugar easily dissolve themselves into. So again, keep in mind that I'm saying that water has both a positive and negative side. So if I put some salt inside enough, let me minimize this video so you can see what I wrote here. If I put some salt, which is a solute, inside of water, which is a solvent, what happens is that Na, because salt is sodium chloride, so sodium is represented by Na and chloride is represented by Cl minus. That's on the periodic table. So yeah, like I said, this has a little, you know, have a little bit of chemistry this time. So anyways, so when you put the salt in the water and you stir it around, physically what you're seeing is that you're seeing the salt kind of disintegrating into the water. But chemically what's happening is that the sodium, which is positively charged, is attracting to those hydrogens with the water. And the chloride that's negatively charged is attracting to those oxygens. So the water is pulling apart all the salt particles, all the salt molecules, and that is why you're actually seeing the water disintegrating into the salt disintegrating into the water. Had you put a substance in there that will not be attractive to water, which is, like I said, is not a lot, but let's say oil or something like a fat, it won't do that. All right, and that is because of the charges that it carries. But most things do dissolve in water, thus it's called a universal solvent. All right, and here is a video that represents that. I might fast forward a little bit because it's very easy to understand what's going on.
What is activated in air, hook up with water, whose molecules divide, soda, and baking soda. First, we will put first molecule soda and baking soda in these 2 cups of water. Stirring for some time. We observe that soda baking soda divide with water. Now we have half soda flour and baking soda in this reaction environment. Starting from the family. We observe that soda and baking soda doesn't divide with water.
All right, so you saw after that last video, so you can clearly see that again, the salt completely dissolves the salt in the baking soda versus the oil does not dissolve the baking soda and the salt, and that is because again water has that positive negative side that's breaking apart those molecules in the baking soda and the salt having it to dissolve. Now let's bring it back to that oil. So the oil with the baking soda and salt, that's considered a mixture. So let me tell you what a mixture is, and to be honest, so is the salt and the water, but we'll get it. I can bring that up in another time. A mixture is when two or more elements or compounds are combined physically but not chemically. If two things combined together can be undone, it's considered a mixture. And just, I guess I can bring it up now. That's why I said the salt water would be considered a mixture. You can undo salt water. But even more so, as you can see, when we did the baking soda and the oil, you can definitely see you can undo that. It didn't even dissolve properly. So again, in the video, you saw that the mixture of oil and its solutes produce leftover material. So that leftover material that was at the bottom, so this is something that the salt water doesn't have. So the salt water didn't have any suspension left over, but the oil did. A suspension, let me take off the video here so you can see it. A suspension is a material that is left over that does not dissolve in the mixture. All right, so that clump that was at the bottom of the cup, that's what we consider a suspension. All right, so let's go over hydrophobic versus hydrophilic because that plays into the next property of water. So the next property of water is going to talk about the basically how attractive water is to itself. So we want to go over hydrophobic and hydrophilic. Hydrophobic, so let's break it apart. So this is why that verbiage worksheet was very important because like I said, as you can see here, biology is a lot of times just breaking apart a word to understand its meaning. Hydrophobic, so hydro means water, phobic means fear of. So hydrophobic means fear of water, literally. Hydro means water again, philic means fond of. So hydrophilic means fond of water. And what happens is if you're hydrophobic, that means that you don't like water. So things like a lipid, oils, stubborn people who don't like to bathe, those are examples of hydrophobic. They don't like water. Keep it away from them. And of course, everyone should know by now that if you put oil in water, it clearly just sits at the top. They do not blend together. They don't like water. Hydrophilic, on the other hand, means fond of water. So salt, sugar, our bodies, those are things called hydrophilic. We like water. Our body needs water. Salt and sugar easily dissolve in water, and so on and so forth. All right, so bringing back in the hydrophilic, water likes itself. So cohesion and adhesion are really big, unique properties of water. A lot of things are cohesive, a lot of things are adhesive, but water is a little bit different. So So cohesion is the attraction between molecules of the same substance. So when things that are of the same substance are attracted to each other, that's cohesion. Water is such a cohesive molecule that it has incredible surface tension, meaning that its surface is so tough to break that it's almost like it's elastic. This property is what causes the formation of a water droplet, or what gives certain bugs the ability to walk on a water surface. So I know you guys always see water droplets all the time and you think that that it's a water droplet, but that's actually a very unique property of water. Tell me the last time you took alcohol and dropped it on the surface and saw that it formed a bubble. Yeah, people don't realize it, but that water drop formation is actually pretty unique to water only. Yeah. And what's happening is that, again, we have that positive and negative charge. So water is very attracted to itself because it has a negative side and it has a positive side. So the negative side is attracted to other positive water particles, and the positive side is attracted to other negative sides of other molecules. So it's constantly sticking and unsticking to parts of other water molecules. Also, adhesion. Adhesion is the attraction between molecules of a different substance. So together the properties of cohesion, so it being attracted to itself, adhesion, it being attracted to other things that are also negative and positive, and the fact that it has a great surface tension, gives water the ability to perform the property called capillary action. This special property makes water so important to plants. All right, so what happens is in capillary action, the water molecules is attracted to itself. The water molecule is attracted to surfaces that are hydrophilic, that like water. So for example, let's say, let's talk about a plant. So what happens is with the plant, the water molecule is attracted to the walls of the plant. All right, so one water molecule moves to the wall of a plant, and because it's also cohesive, the other water molecules say, hey, where are you going? And it starts to flow, and because it's all flowing with it sticking to the side of the plant and sticking to each other, it's like this water is drawing up the plant. Now, think about it. We put water at the roots of a plant and somehow it gets up to the leaves. So this is how this is happening. So with capillary action, what happens is, again, the water molecule touches to the plant's roots, and then it starts to draw up all the other water molecules through the process of cohesion. And then what happens is, as it's all drawing up, it has such great surface tension that the chain is not breaking. So water is literally traveling up the plant to get to where it needs to go. And that's pretty much how that goes. So, and again, water does that with anything, because that's just its property. So again, on this page particularly, we have about 4 properties of water: cohesion, adhesion, really good surface tension, and capillary action. All right, so here's a video that kind of looks at capillary action again, kind of puts it forward to you guys a little bit better.
Today we're going to do a cool water experiment. It's pretty cool. Cool water experiment. This experiment uses the capillary effect. The capillary effect is the aluminum liquid with flows through some salt, often they attract those molecules of the liquid to the level of the salt. For this experiment, we need 2 glasses, colored water, and a paper towel. Next, take 2 glasses, put them side by side. Now, one of the glasses is on the water. Now, grab a paper towel and hold it down the liquid. Just grab the liquid and this goes on the water, and then the other end is the energy right on back. Leave the piece to the back. The water keeps flowing into the other glass, so it is keeping the water.
All right, so before we even move on to heat capacity, so I just want to go over again what happened with the capillary action. So as you can see, he put one side of the paper towel into the colored water, he put the other side of the paper towel into an empty glass, and what happens is so we're using capillary action, so the water molecule adheres to the paper towel, so that's adhesion, and then the water molecule also cohesively bonds with the other water molecules. So they start to pull the water up the paper towel because it's doing the cohesion adhesion. Again, it has such incredible surface tension that it's literally traveling up the paper towel without breaking. And it's traveling. You see, it goes up the paper towel, it goes down, and it reaches into the other glass. Now you're probably wondering, well, why did it not draw up all the water and put it into the other glass? Well, again, like he mentioned, once it got to an equal balance, it stopped. And it's not that it stopped, they're still traveling back and forth. It's just that it's at an equilibrium now. So one side is not going to draw up more water than the other side. No, that's not how water works. Now that they're both balancing, drawing up back and forth, they're at a balance. So they're still moving, but it's just the fact that it's balanced out, so you can't really see that effect happening still. All right, so let's get into heat capacity. So heat capacity is another property of water that's pretty unique. Its ability to hold heat is called heat capacity. Now, mind you, everything has a heat capacity. Your phone has a heat capacity. my coffee has a heat capacity. Everything has a heat capacity. It has an ability to hold heat. Sand at the beach, so on and so forth. But the difference with water is that it's unique, because water's heat capacity is that it's extremely high. So because of the fact that it has these hydrogen bonds, when you're trying to heat up water, they break apart, yes, because that's how you can start to actually heat it up. They start to break apart, but they're so attracted to each other that they constantly are coming back together. So you need to get it to such a high temperature for you to keep those molecules apart. So that's unique to water. Most things, when you start to break it apart, that's it. It breaks apart and it'll stay apart. It doesn't really care. But with water, it'll break apart and constantly come back together. So you have to get to such a high temperature so to keep those molecules apart. All right. So that's that. So that's what heat capacity. Again, heat capacity is not specifically the unique property. The specific unique property of water is that it has a high heat capacity. All right. And then also water density. That's a pretty cool one too. So let me take away my face so that you can see the words. All right, so another interesting property of water is its ability to be less dense in solid form. Again, that's very, very unique to water. Density is a substance's mass per unit volume. Keep in mind, think about it. Water in liquid form is more dense than its solid form. All right, so keep in mind, most things, if you freeze it, it's heavier. But with water, when you freeze it, it's lighter. All right, that's very, very unique to water. I can't even express how unique that is to water. Most things, when it's solid, it's heavy. Look at a bouncy ball versus a bowling ball. A bowling ball is a solid ball. A bouncy ball is full of air, so it's not solid. It's not as solid, so it's very light. Again, when you freeze things, if I had a cup of yogurt and I put it in the freezer, it's going to be a lot heavier coming out of the freezer than when I just take one out of the fridge. Again, that's a unique property. I'll say the unique property of water is that it's the opposite. Water in liquid form is a lot heavier than water in solid form. All right, so again, when most materials freeze, they increase in density, causing most frozen materials to sink. But ice, on the other hand, floats in a glass of water. You probably never actually tuned into that when you had a glass of water in your hand. But of course, your ice floats to the top and your solid water stays at the bottom. And that's unique to water. But this is because hydrogen bonds cause molecules to push farther apart, which lowers the density. So again, this also is the reason why a frozen water bottle loses its shape or expands. I don't know if you've ever wondered why it does that, but that is the reason why. So again, like it's saying, when hydrogen bonds freeze, they move apart. Most things, when they freeze, they move together, solidifying things. But with water, it's different. They move apart and it gets solid. But that's the reason why water is more dense, why frozen water is more dense. And again, that's also why when you put a bottle in the freezer, a water bottle in the freezer, you come back, you take it out, the bottom's kind of popped out or the top pop. And sometimes I've even seen that the water bottle cracks. And again, that is because the water bottle itself, it started to expand. I said the hydrogen molecules expand, and it causes for the plastic to lose its form and lose its shape. And that's how that works. So here's a video to kind of show you that it's a unique property of water. So that's alcohol, and he's putting it into the beaker. That's water solidified. Ever seen that before? Always see ice floating, right? But in alcohol, it sinks. Now he's putting water into a beaker. So again, ice inside of water, liquid water, it floats. Ice inside of alcohol, it sinks. So solid ice is denser in alcohol, but solid ice is less dense inside of liquid water. All right, so let's talk about water as a universal buffer. Now, before we even get into the slide, I kind of want to just give you the summary of this because you already know this. Anytime I said, look at some of the products here. If you had some, let's say some vinegar, right? And nobody drinks, I said, well, some people do. There's the whole apple cider vinegar thing. But if you wanted to, because the vinegar is very strong, it's very, oh my God, it's harsh if you try to drink it by itself. Naturally, if you want to dilute something that's really harsh, what do? You add water. Same thing. Household products like bleach. If you feel like the bleach is too strong for certain surfaces, what does your mom or what do you do when you're cleaning to dilute the bleach? You add water. So that's what it means that water is a universal buffer. All right. So okay, the pH scale is a measurement system that indicates the concentration of hydrogen ions. So again, you have the basics and you have the acidics. So your acid side is those guys that are less than 7. Your bases are more than 7, and that's the pH scale. And it also gives you kind of some things in your everyday household that you can easily compare to what's basic versus what's acidic. But again, the key thing with water is that it's a universal buffer. Notice that on the pH scale, water is neutral. All right, and this is for a reason. Buffers are weak acids or weak bases that help to kind of regulate the strongness of some of the products that you see. And again, that's why we use water as a buffer. If you add water to anything, it will kind of neutralize that. So the more water that you add, the more neutral it is. So of course, like I said, it's very common sense. If something is too sweet, what do? Add water. If something's too salty, what do? Add water. Again, water is very known to be a universal buffer. Again, right now we're just adding vocab to it, so that's why it seems new to you guys, but it's very, very simple to understand because you understand that in your everyday life again. So that's that for that one. So that's that unique property, and that is our last unique property of water. This is the Amoeba Sisters. They also go over properties of water. Feel free to watch that video. It's really good. That's why I included it here. And that concludes, I believe, our property. And we're on to macromolecules. Bye, guys.